Hello and welcome to yet another video of signals and systems. And in this video, we'll be discussing the basic operations that can be performed on the signals. We have dealt with the mathematical model of the signal, that's x of t, and then we have done some classifications of the signals. The next is the basic operations that can be performed on the signal. Now from the previous videos, we have come up with a mathematical model of a signal, and we have defined signal as x of t as the amplitude variations with respect to time. So we have taken two variables. One is the independent variable, which is the most important variable, that is the time. Mainly it will be time. Then we have the dependent variable, which is the amplitude of the signal, or sometimes the intensity of the signal. Accordingly, there are basically two sets of operations. One is the operations that are performed on the dependent variable, that is amplitude in our case. These are not that important, but there are some operations that can be performed, that are performed on the dependent variable, although their significance is not that much. Then we have a second class of operations that are performed on the independent variable. That is the operations that are performed on the time variable of our mathematical representation of a signal. Now these are important because it's an independent variable. They have a lot of significance. So first of all, we will consider the dependent variable, that is the operations that are performed on the dependent variable. And there are few, like we have amplitude scaling. And amplitude scaling, it simply means that the amplitude of your signal, it is being scaled by some factor, fine, some constant, that is. So I can simply mathematically represent it that if I have a signal y of t, let's do one thing. I have the original signal in the continuous time domain as x of t. Then I have some scaling factor, that is a constant. Let's call that c. Then I can define my amplitude scaling as simple multiplication of this constant to the signal x of t. Right? The simple operation. Similarly, if you're talking about discrete time domain, so it will be y of n, c will be scaling factor, and you're multiplying this scaling factor to each and every sample. Right? So depending upon the value of the scaling factor, it will accordingly modulate your amplitude. If the scaling factor c is greater than 1, then the amplitude will increase. For example, if c is 2, you will have y of t is equal to twice x of t. So the amplitude of your signal will increase. And in case if it lies between 0 and 1, for example, if c has a value of 0.5, that's 1 by 2, it will reduce the amplitude of your signal. It's a simple operation. Fine. Similarly, we have addition. Addition is that we have two signals, say x1t and x2t. Then we define a new signal y of t as the sum of these two signals. Right? Again, since it is the sum, so the amplitude will add up. Then again, in the discrete time domain, this will translate into this thing. We have x1n and x2n as two discrete time sequences, and we add them sample by sample, and the amplitude will increase of the resulting signal, that is y of t or y of n. Right? It's again a simple operation. Then we have multiplication. Again, if I have two signals, again say x1t and x2t, then we define a new signal y of t as the product of their amplitudes. x2t, and in the discrete time domain it will be x1n dot x2n. Fine. So these are some simple operations that are performed on the dependent variable. Fine. And they have some implications, like this multiplication of two signals. When you will go to the next class, you will be studying amplitude modulation. That is a modulation scheme that actually works on the amplitude of the message signal, and we can achieve amplitude modulation by simply multiplication of two signals. One will be your message signal and the other will be your carrier signal. Fine. So these are some simple operations. Like I said, they're not that relevant, they're not that significant as compared to the operations that are performed on the independent variable. But these are some operations that you can perform on the dependent or the dependent variable, or simply the amplitude of the signal. But an important class of say basic signal operations, it is the operations that we performed on the independent variable, which is time. So independent variable, we know it is time, and we have three basic operations that are very important with respect to their independent variable operations. First among them is time scaling. Fine. We earlier had amplitude scaling, so you are basically scaling the amplitude of a signal. But in time scaling, as it is quite literal, we will be scaling the independent variable, which is the time t of a signal. So originally, if I have a signal x of t, I can time scale it by multiplying the independent variable with some scaling factor a. Now the thing is, what will be the implications on the signal? What will happen to the original signal x of t in a general manner, that is. So there are basically two cases: that if the scaling factor, let's use this a so that we can differentiate. If the scaling factor is greater than 1, then the signal, that is the resulting signal y of t, it is actually a compressed version of the original signal x of t. Fine. And I can easily show it by means of a waveform. Suppose I have a signal, so this will be my time axis, this will be the amplitude axis, x of t, and let's suppose the signal is something like this. It ranges, it is between two time intervals like this. Fine. Let's suppose the signal is defined between 2 points -1 and +1. This is x of t. And let's suppose that a has a value, my scaling factor has a value of 2, so that my resultant signal y of t is x of 2t. Right? Which means the value at y of -1, it will be x of -2, just doing simple substitution. Similarly, y of say -1/2, it will be x of -1. Similarly, y of 1/2, it will be x of 1, and y of 0, it will stay at x of 0. Now if I try to plot this signal, the scaled version, this is my amplitude axis, this is my time axis, so this is time. Now this will be y of t, which is equivalent to x of 2t. Fine. The central point, it stays the same, that is y of 0 is equal to x of 0, so it will stay the same whatever the value was. But y of -1 is x of -2, but x of -2 is 0. So if I kind of let me just try to project this. Projections. So the value y minus 1, that is this, it is x minus 2, but x minus 2 is 0, so we don't have any value here. Y of minus 1 by 2, which means somewhere here, is x of minus 1. That is a value which was here. So it will start from here, reach to some point, this say here. Similarly, on the other hand, y of 1 2, y of 1 by 2 is x of 1. That means here, something like this. So this is 1 by 2. Then again, y of 1, it will be x of 2, which is not defined, which is 0. Okay. So as you can see, you can easily visualize this, that I have compressed my signal. Earlier the span was large, it was defined from minus 1 to plus 1. Now if I use a scaling factor a greater than 1, the signal is being compressed between minus 1 by 2 and 1 by 2. So in general, if the scaling factor is greater than 1, the signal, the resulting signal, this time scale signal, it will be a compressed version of x of t. Similarly, the other way around, that if 0 less than a less than 1, then it will happen the other way around. The signal y of t, it will be an expanded version of x of t. Right? So the signal will expand. Okay? इसका जो time span होगा, that time span, it will be greater if it lies between this range 0 and 1. Negative values, that is basically another operation which will be taking after this. That is, it's called a reflection, yeah, folding. But for the time being, we'll consider only the positive values of the scaling factor. Greater than 1, your signal will compress. If it lies in the range 0 to 1, your what you call the signal, it will expand. Fine. Now what will happen in the discrete time case? So mathematically we can just project the same thing, that in the discrete time case, so in the discrete time case, I can write y of n is equivalent to x of kn, where k is the scaling factor. Now in the discrete time case, we only deal with the discrete time intervals. N is an integer value 1 2 3, and the same thing applies to k. That is, it cannot be a fraction, it has to be greater than 0. That's 1 2 3 4 5 6, something like this. Okay. So if I take a typical example, again I will just randomly plot a discrete time signal here. So this is my amplitude axis, now this is my time axis, but a discrete one. So this is n, this will be x of n. Then there are discrete, so this is 0, let this be 1, let this be 2, let this be 3 4 5, and we can also go along the negative axis like this. Then there may be some sample values, say this is a sample value here, then let's suppose 1 pe hai, 2 has a value this, 3 has this, 4 has this, 5 has this. Fine. So it is defined from -4 to 5 at discrete time intervals. Now let's suppose I take a typical value of k, say k has a value of 2, and I am trying to plot the signal I am trying to plot is Okay, this will be again n, and I am trying to plot y of n, which is x of 2 times n. Fine. Again, you can just do some rudimentary calculations. I can simply construct a table just to find the sample values. If n has a value of 0, that is y of 0, it will be x of 0. Then if n has a value of 1, that is y of 1, it will be x of 2. Similarly, if n has a value of 2, y of 2, x of 4. Here likewise, if n has a value of say 3, then y of 3 will be x of 6. If you go to the negative axis, -1, y of -1 will be x of -2. -2, y of -2 will be x of -4. Then -3, y of -3, x of -6. Okay. So let's try to plot. So this is 0, this is 1, say this is 2, this is 3, -1, -2, -3. y0 is equal to x0, so whatever is the value here, same value will appear here when n is equal to 0 is concerned. Then a y of 1 is x of 2, so y of 1 is x of 2, so this value will appear here. Then y of 2 is x of 4, y of 2, x of 4 is this, something like this. Y of 3 is x of 6, x of 6 does not exist, so no value here. Y of -1 is x of -2, y of -1 is x of -2. Then likewise y of -2 is x of -4, y of -2 is x of -4. Then again y of -3 is x of -6, which does not exist. So the clear-cut observation is that in the discrete time case, if your scaling factor is greater than 0, you will lose some samples. Fine. So let me just put out here. If scaling factor is greater than 1, that is k greater than 1, and since k is an integer, it can only have values like 2, 3, 4, 5, 6. So in that case, some samples in the original signal will be lost, like in the example we just did. Original signal at home made 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sample values, while as the reconstructed signal after time scaling has 1, 2, 3, 4, 5 samples. Okay. So in the continuous time case, if a is greater than 1, that is scaling factor is greater than 1, it will lead to the compression of the signal. And in the discrete time case, it will lead to the loss of the samples. Fine. So we'll stop here this video. Next video will take other operations.